Welcome back. This is homework 1 in thermodynamics 1. Homework 1 is associated with chapters 1 and 4 of Koretsky's thermodynamics textbook, which is basically pure properties, some basic thermo stuff, phases, and basic concepts of equilibrium, and also equations. And then chapter 4 is equations of state and intermolecular interactions and such. So this is problem number 4, which is also taken from Koretsky. Koretsky's problem 1.15. So Koretsky's problem says, consider two systems of ideal gases. And so the first thing we do is we always kind of recognize the problem. If we have tough time recognizing the problem, though, we skip to the second stage and then come back to the first stage. Second stage is always draw a picture. Okay, so if we're going to draw a picture, we have two systems of ideal gases. Okay, and we also want to always include our assumptions. So we're assuming here everything's an ideal gas. Okay, so system 1 consists of pure A. Okay, and it's at a given pressure and temperature. Okay. System 2 contains A and B at the same temperature and pressure. Okay, so the temperature and pressure are equal between the two. Okay. Let's see here. So it consists of pure A given pressure. If the molecular weight of B, so the molecular weight of B is greater than the molecular weight of A, how does the molar density, which is N divided by volume total, of 1 compare to 2? Okay, so I draw my picture. I've written down what I know. I've got A's in there, I've got A's and B's in there. The temperature and pressure is set there. It's the same temperature and pressure set there. Also, my molecular weight of B is greater than my molecular weight of A. And then I write down what I need to find. Okay, I need to find my molar volume and compare the two. And again, my molar volume here is molar density is moles per total volume. Now, it says that the well, it actually doesn't say anything about how many moles, but it also doesn't say anything about the total volume. So really, I have to depend upon the actual, I have to think about the actual equation of state, which in this case is PV equals nRT. Okay, and so let's rearrange this so it matches that. So I have N over V total equals, let's see here, P over RT, okay, yeah, all right, okay. Now, what I'm noticing here though, well, maybe you already notice it. What role is the molecular weight playing in the molar density? It's not. This has nothing to do with the mass density. This just has to do with the molar density. And the molar density is only dependent upon pressure and temperature and the gas constant. Now, of course, the gas constant is constant. So we have to compare the pressure and the temperature of the two different systems. But what did we already say about the temperature and pressure? That's right, they're the same. So pressure's the same, R's the same, temperature's the same. So N over V total as a ratio has to be the same. Now N might be different and V total might be different, but that doesn't matter. As a ratio, they're the same. And you might be, there's A's in that one, there's B's in that one. It doesn't matter, because how do we define an ideal gas? No interactions, no attractions, no repulsions. Every molecule in an ideal gas thinks it's the only thing in the universe. It's all by itself. It owns the universe. And so that A, in terms of that 1 mole of A, has all this volume to it, and it's not sharing it with nobody. And the B thinks the exact same thing. But the A in the first system thinks the exact same thing. The perspective of A has not changed in between the two, and neither has the perspective of B. The perspective of B is, I'm the only thing in the universe. So it doesn't matter that there's A and B versus A and A, because they don't see each other. Okay. All that matters is what the ideal gas equation of state says, and they say the exact same thing. Now you might be asking yourself, all right, what about the mass density? Okay, that's where things do get different. We still have this, but we need to figure out how much moles we have. Okay? Now, molecular weight divided by, the mass is equal to molecular weight times moles. Okay? And so this becomes, to get N is basically M over molecular weight V total. Okay. Okay. And the mass density is really this M over V total, so P over RT really becomes rho over molecular weight. Okay, and so now, well, this is constant, but this is different. So really, the rho of system 1 is basically proportional to the molecular weight of system 1. Okay, and the rho of system 2 is proportional to the molecular weight of system 2. Okay, so really, if the molecular weight's bigger, the density's bigger. That's what it boils down to. Okay, so molecular weight of B is bigger. All right, so that because this has more B, it's going to have a bigger mass density, and that's it.